Last time we admitted we'd been cheating. We wrote load, add, store, but that's not what the CPU actually sees. In reality, the CPU sees this. 8 bits per instruction, patterns of ones and zeros. This is machine code, the real thing. It's what gets loaded into memory, what the CPU fetches, decodes, and executes. But look at it, can you tell which instruction is load, which is add? This is why we need a better way to write programs. What if we could write human-readable text that maps directly to these bits? That's exactly what assembly language is. Load, add, store. These are called mnemonics, memory aids. Each mnemonic maps to exactly one opcode. The numbers like R0 and bracket 10 are operands. They tell the instruction what to work with. One line of assembly becomes one machine instruction. No more, no less. This is the one-to-one mapping that makes assembly special. But there is still a problem. Look at those addresses, 10, 11, 12, 13. What do they mean? Which one holds the first number? Which holds the sum? What if we could give them names? With labels, the code can tell a story. Load num1, add num2, add num3, store to sum. Labels aren't just for data, they work for code addresses too. Instead of jump to address 1, we write jump to loop. The label marks a spot in memory. We can reference it by name. But the CPU still only understands binary. Someone has to translate. That someone is the assembler, a program that converts assembly to machine code. Assembly has a beautifully simple structure, one line, one instruction. Each line follows a predictable pattern, an optional label, a mnemonic, and operands. This makes parsing trivial. The assembler reads line by line, splits each line into parts, and looks them up. High-level languages like Python or C have much more complex syntax. They need sophisticated parsing, but that's a story for later. The assembler works in 2 passes. Pass 1, scan for labels and record their addresses in a symbol table. Pass 2, translate each instruction, replacing mnemonics with opcodes and labels with addresses. 1 instruction in, 1 instruction out. Perfect one-to-one translation. There's one more thing assembly gives us, comments. Everything after a semicolon is ignored by the assembler. Comments are for humans. They explain the why behind the code. Machine code can't have comments. It's just bits. Assembly can, and that makes all the difference when you come back to code later. Let's see the complete transformation. First pass, build the symbol table. Start is at address 0, loop is at address 1, result is at address 20. Second pass, translate. Load becomes opcode 0000. The 5 is the immediate value. Same program, human readable on one side, machine executable on the other. The assembler bridges the gap. From NAND gates, we built a CPU that executes binary machine code. Assembly language sits just above, a thin readable layer with one-to-one mapping. We can write programs, we can use labels for organization, we can add comments for clarity. But there's still a problem. What happens when we want to reuse code? What if one piece of code needs to call another, then come back? Next time, the stack, how functions call each other in return.